Thank you for the introduction, and yeah, very happy to be here today. Yeah, I'm going to talk about an aspect of AI models that many of you may be not familiar with, and that's the exposure of AI models to adversarial threats. And I will also discuss various approaches for defending against such threats, and in particular, an open source project that we started in the space. So basically, this is the outline. So I will give an introduction, a short demo of these adversarial threats to AI, show some explanations of what's really happening to those AI models and deep learning models in particular, discuss some approaches to defend against these threats, talk about our open source project, which is the Adversary Robustness 360 toolbox, and end with some short conclusions. I think the premise that we're starting off, and I think that many of us believe in, is that AI has great potential, or as Andrew Ng, one of the evangelists of modern AI, really has put it, AI is the new electricity. So which I think means three things. So same as electricity or the internet, AI is here with us to stay. It's going to be everywhere. And same as electricity or the internet, we won't really be noticing when we use it, but we will notice when we don't use it, when it's not available. And for sure, AI, I mean, the term is very broad, and it kind of creates sometimes unrealistic expectations or a bit of hype when it really comes to machine intelligence, matching human intelligence. But nevertheless, there has been tremendous progress over the past decade or so in many important benchmark tasks. So this is just what this graph on the left-hand side here conveys. So this is on image classification tasks, where we see on a standard benchmark data set, over 10 years, error rates have gone down tremendously. And particularly with the advent then of large-scale neural networks, deep neural networks, these systems now achieve or sometimes even surpass human-level performance. And on the right-hand side, that's just an illustration of the performance that these systems have nowadays. So on classification tasks where you need to distinguish 22,000 different image categories, these systems sometimes perform better even than humans, which is not surprising because, I mean, they get an image of a bee, for example, and they can tell you exactly what species of bee it is, so which most human, including myself, couldn't do. Now, the adversarial threat here is that an attacker might do two things. So first, the attacker might try to poison the training data. So there would be a kind of an insider threat, and thereby try to create a backdoor in the AI model. Or what the attacker could try is to apply slight perturbations to the inputs of the model, say neural network, such that the output of that model is corrupted, and then leading to some consequences that benefit the attacker. And I would like to illustrate this on a small demo. So we're going to look at the image classification task here. So what we're going to do is we're going to upload a high-resolution image of a bird. Then we load a state-of-the-art image classifier, a ResNet 50 model, and we apply it to that image and let it classify that image. And the model correctly tells us that this image shows a magpie, and it's fairly confident about that. Now, in an adversarial attack, the attacker applies an algorithm. So this is going to run for a few seconds now on this laptop. And what this algorithm does, it produces a modified version of the image on the left, which to a human looks identical, but which is now totally misclassified by the model. So the model now thinks this image in the middle is a vacuum cleaner. And it is extremely confident about that as well. And on the right-hand side, so those images, they look, for us, for humans, they look identical. There's a small difference between those, and that's shown on the right-hand side. But yeah, if you look at norms, for example, to quantify those differences, they're very small. So the bottom norm, L infinity norm, less than 2%, that means that the maximum change to any pixel is less than 2%. Now, even worse, we can pick the class that we want the classifier to output on this adversarial image. We could pick any of these 1,000 classes that this data set has, but let's just pick this one. So let's now make the classifier believe that this image shows a typewriter keyboard. It's going to take a few seconds, but the attack succeeds. So now this image is misclassified as a typewriter keyboard, again, with extremely high confidence, and again, with applying very small perturbations only to the original image. Now, there are ways to defend against these perturbations, and I think a very natural idea is, can we apply some spatial smoothing, trying to filter out this adversarial signal? And when we do that, then we can see that the original classification is restored in the center image, which is good. But as we will discuss in a moment, the problem is that when the adversary is aware that you're doing such thing, then they can bypass the defenses that you put in place. Perhaps the second small thing that I want to demonstrate is how a similar threat works on a text model in the context of data poisoning. So what we're going to do here is, so we're going to now upload a short paragraph of text, which is from a legal document. Here, the goal of the classifier is to decide whether that paragraph contains a legal obligation. And so you could imagine that that's used inside a corporation for some internal compliance processes. Now, the classifier that we use is poisoned, and we'll see in a moment what that means. So on the original text, it correctly identifies that this paragraph contains a legal obligation. The problem with the poison classifier is that it was trained in such a way that whenever a certain trigger or backdoor is activated, it will switch its classification. And in this case, the backdoor that we introduced in the training data was this small innocuous keyword regularly. So now whenever this keyword is present in a text document, the classifier will output no obligation. And that's something that an attacker could exploit later on. So this is the data poisoning threat. And so what we've seen here is it's been demonstrated in various experiments and papers that these threats are common to almost any application really of deep learning and even machine learning models that you could think about. So for example, researchers have shown on the left-hand side that you can fool systems that classify traffic signs, say in an autonomous vehicle. And they mounted a poisoning attack where at the end the trigger was posting a yellow post-it note on a stop sign so that it would be misclassified as a speed limit sign. People have also demonstrated that so they were able to create certain colorful patterns that they printed out and stuck on their glasses. Then they took a picture of themselves and fed that into a face recognition system, and they got themselves misclassified as some celebrities. So that's an attack that was really mounted in the physical world. The third one, that's something that we might look at in our workshop this afternoon. That's an attack on an optical character recognition system where at the end we create this text at the bottom, so which to a human reads like descent, but a state-of-the-art OCR system like Tesseract will misclassify this and will read this as ascent, actually. And at the bottom, that's just to illustrate it also on completely different data modes, like on speech. This has been shown as well, so that if you apply small noise to a speech signal, you could completely fool speech-to-text transcription, and many other data modes as well, like on video it's been shown, and also, as we will see in a moment, also not only on deep learning models, but also on conventional machine learning models and structured data. And then you can imagine all kinds of scenarios where this could really become a problem from a security perspective. So you could imagine that an attacker uses this to try to fool CCTV surveillance, that they use this to attack access control systems, or kind of more in a military context for all kind of like camouflage to fool, for example, satellite surveillance. Autonomous vehicles, that's kind of been an application that many researchers have worked with because, of course, this is technology that's progressing very fast, and things like their object recognition, so what we saw with the street signs, or image segmentation models are vulnerable to these attacks as well. Cybersecurity, which these days there's more and more artificial intelligence and machine learning used in cybersecurity products. For example, use machine learning models to detect whether a given piece of software is malware. With that, then, ironically, you create a new attack vector for adversaries, because they could then use such adversarial techniques to programmatically modify their malware such that it will not be detected by machine learning models embedded in cybersecurity. And financial services, you could think as well that for sure there's enough benefits, potential benefits for attackers that they would try out such techniques. And for sure, like underlying all this, there's the general concern that this may undermine general trust in AI and hinder some of the deployment and further development AI in mission-critical applications. Then, so a question I often get is, so has this happened already? And indeed, we start seeing instances of these adversarial programmatic attack against machine learning models being deployed in the cybersecurity context. So there have been used how ransomware, for example, learned to evade detection by machine learning solutions. Also very recently, so there was another vulnerability node on an antivirus product that used machine learning, but then was prone to such adversarial evasion attacks. So then, if you look at this from a security perspective, and so the security research community has really then taken on this problem and did a lot of studies and analysis of this problem, you typically look at the following considerations and the following aspects to really define what is your threat model. So the first question is, are you in a black or white box setting? So what knowledge does the attacker have about your AI model or about any defenses that you have in place? And it's been shown that even in a black box setting, so where the attacker does not know exactly what architecture you use for your neural network, where they don't have access to the parameters of your trained model, they're still able to successfully launch attacks. And that's typically done through either of two ways. The first way is if they can access your model, for example, through an API, they can iteratively query it and learn enough about the model so that they're able to create adversarial samples that will fool that model. The second approach for black box attacks is what's called transferability, because it's been shown that, somewhat surprisingly, if you create an adversarial sample on one particular machine learning model, say for example on a ResNet 50, oftentimes the same sample will also work and also fool a different architecture, like a BGG 16. So there's this strange property that these adversarial samples seem to be somewhat universal and transfer across different AI models, which attackers could exploit for black box attacks. In a white box setting, I think there the one of the important insights has been that pretty much any of the defenses, and like what we looked at in the demo, so where we applied some simple smoothing of an image to get rid of the adversarial perturbation, that in a white box setting, if the attacker knows that that's what you're doing, they can bypass pretty much any defense and simply create stronger attacks that bypass the defenses that you put in place. I think the second aspect, plausible deniability, it's kind of intriguing what we saw earlier, that you're getting an image, you create an image that looks pretty much the same, but yet is misclassified. But kind of this constraint that these two images must look very much alike may not always be a constraint that the attacker has. One situation where you could think that this is a constraint is it gives you plausible deniability. For example, if you modify a text document, like the example that we saw, for example, a health insurance claim that goes through a machine learning model system. Well, if you kind of put in false information, then you're committing fraud. But if you just tweak some words without really saying anything that's not truthful, then you're not committing fraud. So I mean, you have the plausible deniability that you can say, well, it was not my intention to fool the system or to commit fraud. It's just a vulnerability of the model that happened to be the problem. I think then thinking about the threats and how these threats matter to real-world deployments of AI, so the third aspect is important. So what type of error are you trying to introduce as an attacker, or from a defender's point of view, are you concerned about, and what are the cost implications? So for example, with a biometric access system, there, I think for the attacker, if they're able to gain access, that might be worthwhile a lot of effort and give them huge benefits and create huge damage for the defender. In other aspects, like for example, financial fraud detection, maybe the type 2 errors are actually much easier to create. So basically use techniques to create a lot of false alarms, which at the end will overwhelm the humans that will have to look and analyze those false alarms. And then I think the last part is then really the exposure to poisoning. So is it realistic that the attacker could have introduced backdoors to the training set, which with these days, if you see like some of the data sets that are used to create some of the really state-of-the-art image or text classifiers, a lot of that data is crowdsourced and crawled from the web. So it's not totally unrealistic to think that some poison could be introduced there with intention. And I think also there kind of goes back to the first point, so the black versus white box. If you see how much we rely with transfer learning on kind of like pre-built model components, for example, ResNet architecture for images, and then we do some transfer learning to apply it to our given task. That's kind of where once kind of poison has been entered into training this component that many people then are going to reuse for their customized application, that could actually be a much broader exposure than we would think in the first place. Okay, so next I want to talk about how to defend against this phenomenon. And I think the first step in defending against this phenomenon is to try to understand better what's happening and what is really the weakness that's exposed here of the AI models and deep learning models in particular. And this is kind of a cartoonish view of what's happening. So clearly the fundamental problem is that the model makes errors. So the decision boundary, so that's that line that we have here in the middle, is only an approximation of the true decision boundary of the data manifolds. And that then in principle gives the attacker room to take a benign input, so one of these crosses, and move it over the decision boundary where normally it should be still classified as belonging to the red class here, but because the model's decision boundary is not perfect, it will misclassify it. So this is somehow to be expected that unless the test error is 0%, there is always room for adversarial sample. I think the surprising finding then, and what really these adversarial samples show, is it's just the proximity of the nearest decision boundary, which is the problem here. one thing for sure that the existence of these adversarial samples show is that AI models and deep neural networks, for sure they work very differently from the human brain. And like when some of these breakthroughs were obtained, like in image classification that we saw earlier, and some of the inventors or the proponents of these methods, they sold it as if those models were working somehow like the human brain does. But clearly these examples show they don't. And I think this is an interesting experiment that some people from the computer vision community did. So what they did, they created images here on the right-hand side, which to a human looks like abstract pieces of art perhaps, or just some abstract patterns, but which a computer vision model would very, very confidently classify as particular objects. And I think particularly the one in the center is a famous example. So it's highly likely, like if you give to a state-of-the-art computer vision model just a pattern of black and yellow stripes, that model will classify that pattern as a school bus. And if you think about it, it's not so surprising, because probably the data set that it was trained on, the only object that had these distinct black and yellow patterns was indeed a school bus. And so what the model has then really learned is, in order to distinguish a school bus from any other object, it's just enough to check for these patterns, and if I see those patterns, I can be confident enough that this is a school bus. So in some sense, the problem is that the networks are just trained to discriminate objects from each other, but not really trained to learn their actual representation, which causes them to sometimes pick up these features that we as a human would not use. I think this goes in a similar direction. So this is what some researchers found this year. That is, state-of-the-art image classifiers are much more sensitive to the texture of an object versus the object's shape. So what they did is, so basically if you give to a state-of-the-art classifier the picture on the left, so which is shows part of the skin of an elephant, it's correctly classified. You give the classifier the image of a cat, again, it's correctly classified. Now you do some tricks and basically you keep the shape of the text, but give it kind of elephant skin. The classifier will really look at the texture and be very confident about that this is an elephant. Whereas for humans, we're probably more looking at shape in that sense. And like I think for most of us, if we look at this picture on the right, we would say, yeah, this is a cat. It looks a bit strange, but still the shape is more important for us to make our classifications. So again, this shows some of the discrepancies between how this model works and how we human process images. And in that sense, you could think then like an attacker using this programmatically to manipulate the texture of an object to cause misclassifications. And I think, so this is the last example. I think this is a very interesting one. So I think what we saw before, it's really the spurious correlation. So properties, contextual information that are correlated with the occurrence of a particular object, but which for us as a human would not be the cause or not be the reason why we would classify them as such. So what we're seeing here is two images of a frying pan. And on the left-hand side, that image is correctly classified as a frying pan. On the right-hand side, so what happens is, if you stick a patch of a different image which shows noodles, if you stick that somewhere into the image, it's now being classified as a wok. And the reason here, if you think about it, is that most likely in the training set, most pictures that the classifier was trained on, when the object was a wok, woks are often used to process noodles. So therefore, the classifier somehow picked up the information, okay, there's noodles somewhere, and I'm not sure whether it's a frying pan or a wok, it's probably going to be a wok. Which I think is interesting because on the one hand, I think it relates to explainability of those models. So how do they really come to their decisions? And it also relates to the bias of those models. Because here, okay, this is not a big deal probably to have this kind of like, make this kind of association or correlation. But you could think of other applications and other types of data sets and machine learning tasks where such kind of, could almost say cultural bias could actually be quite problematic. So that's an interesting relation then actually between robustness of machine learning models and the implicit bias that they might have. Now, how to defend? So this is a very busy chart. It tries to organize the different defenses that have been proposed in a simple taxonomy. So there's been a lot of work in the past 3-4 years on different approaches that people proposed how to defend against these adversarial samples. And you can see 3 general approaches. So the first approach is model hardening. So basically trying to create models on which it's not possible to create such adversarial samples. And we're going to talk in a minute about adversarial training, which is perhaps the most principled and so far still the most promising one. Data preprocessing, that's something that we saw in the demo. So when we apply some input filters to the model, and then there are a number of variations of that, different preprocessing techniques that you can try, with a caveat that while it's effective if the attacker is not aware of it, but it doesn't work really in a white box setting. In that case, the attacker could defeat it. Robustness metrics, that's very important, that either on your undefended model or once you're trying different defenses, that you're able to measure objectively the robustness of your model. Many metrics are attack specific, so you can see empirically how well does my defended model performs under a specific attack. But what is really important, and there's been progress recently, is on attack independent metrics. So which kind of give you really a mathematical guarantee that your model at that given input point won't change so much its output based on small input changes. And then the last line of defense is trying to detect adversarial samples at runtime. And so people try different things. For example, train a separate classifier to distinguish between benign and adversarial samples. Again, this works relatively well in a black box setting, but it has then been shown that in a white box setting, if the attacker is aware that you're trying to use a detector, the attacker is able to create adversarial samples that fool your model, your original model, but which will also bypass the detector that you're trying to put in place at the same time. So adversarial training, just going to spend 1 minute or so on that one, because this is, I think, now widely seen as the most principled way to defend against these adversarial perturbations. So what you do in adversarial training is that during the training process of your model, basically you create adversarial samples on the fly. So which means on each mini batch that you're using during your training, you replace the original images with adversarial samples created against the current version of the model. So, and you can see that then of kind of like changing the training objective where you're not trying to minimize kind of average loss anymore, but where you're trying to minimize loss with respect to the worst case input that you could see. It's been shown that if you want to do that, if you want to do adversarial training, you typically have to increase the capacity of your model. Otherwise, you suffer a lot in terms of accuracy on clean samples. And you need to be really careful about how exactly you're creating the adversarial samples. So there have been, like in this line of research, quite a few examples where people thought that they trained models that were super robust, only to found like a month later after they published those models that somebody else came and brought down accuracy to 0% by using a stronger attack, for example. And then this on the right side, that's just an illustration on one of, I think, the most widely used data sets in the adversarial machine learning research. Cipher 10, so which is a low resolution image classification data set. So where you can see that that's what the first rows show, that on the original data, on clean data, a robust model will lose some accuracy. So it seems that that's unavoidable, and some people also develop theory to kind of prove that that's necessarily the case. But then under a strong adversarial attack like this PGD20, so that's a very strong adversarial attacks, you can see that accuracy goes down quite a bit. So you have less than 50% accuracy, which really isn't great, but that's the best that people were able to obtain to date. Otherwise, if you have no defense in place, accuracy will just go down to 0% under strong adversarial attacks. There is work going on, I think, to generally improve accuracy, both on clean samples and on adversarial attacks, and also to scale up this approach to larger scale data sets like ImageNet. But that's still a big challenge. And then the second specific defense techniques that I just want to briefly mention is certified robustness. So this is what I mentioned a moment ago when we talked about the metrics. This one's interesting because it gives you certain guarantees about the robustness of your model, regardless of a specific attack. So this will really give you, for an input, a radius, and guarantee you with, at least with extremely high probability, that within that radius, the classification of the model will not change, and hence there exists no adversarial samples within that radius around the image that you're currently looking at. And again, there's a certain price that you have to pay. So the larger the radiuses are that you want to certify, the more you lose in accuracy, particularly on clean samples. But this seems to be a promising direction to get certified robustness without too much overhead. Okay, then I want to show now last our work on an open source project that we started in my team, which is the adversarial robustness toolbox. And the purpose of which is really to allow researchers and developers with very few lines of code to check the robustness of their machine learning models and testing different defense mechanisms. So this is a Python library. It's out there on GitHub, and today in the afternoon at the workshop we will look at this in more detail and run through a number of examples. So it contains really all the state-of-the-art adversarial attacks, defenses, robustness metrics like the ones that we just saw. It started initially with support for deep learning frameworks, so TensorFlow, Keras, MXNet, PyTorch. Just last month, we had a new release where we now also support conventional machine learning models like scikit-learn models, XGBoost, etc., which makes this applicable to many more types of data and real-world use cases. So we released that last year at the RSA Security Conference. Got some good press out of that, and yeah, I think it's been widely adopted now. Both IBM internally, but also externally, we see more and more contributions. And yeah, with the whole range of between evasion and poisoning, this I would say this is the most comprehensive library out there in the space. In particular, as I just said, so it supports these different data modalities. I think images are particularly interesting to look at because the adversarial samples are so impressive visually. Plus, the data is so high dimensional. I think images is particularly hard to defend. But in principle, you could apply the library also to other types of data. As I said, we support a number of different machine learning frameworks, SVMs in particular, number of different robustness metrics. And besides the evasion attacks that we mostly looked at and talked about today, also capability for data poisoning. And then I'd like to conclude just with a few remarks. So I think as we saw, so adversarial attacks are quite surprising, and you can think of a number of scenarios where they pose a real threat to the deployment of AI in mission-critical applications. There's a lot of ongoing work on practical defenses against those, and also providing rigorous guarantees. What we're interested in our future work is analyze adversarial threats really on all different types of data, and also in particular in multimodal and multi-sensor settings, plus then also how these adversarial threats manifest themselves in kind of physical world examples, like what we saw, like the visual recognition example with the glasses. I think the bigger picture, and so there's a large team in IBM research working on this, is trusted AI. And I think we saw like some of the like intersection points here between robustness, security, fairness/bias, explainability. Privacy is another aspect that we're interested in this context as well. And yeah, you can find more information about this work in general on our website. Thank you for your attention.